Hi everyone, and welcome to Unit 3 of Pre-Calculus. Today we are going to talk all about angles, specifically some vocabulary, talking about standard position, initial side and terminal side, as well as identifying the coterminal angles. Okay, and today we are going to start on page 187 in your Springboard books. So if you look here on that first page, we kind of have a little bit of a review of geometry, which is going to be a lot in activity 14 of what we do. So reminder, an acute angle is an angle that is between 0 and 90 degrees, but it's not going to equal 90 degrees. It's got to be less than 90. Obtuse angles are angles that are between 90 and 180. They're not, again, going to equal 90 or 180. Right? 90 and 180 are reserved for our right angles and our straight angles. Our right angles equal exactly 90. Straight angles equal exactly 180, right? And I do have a fun angle song. If you remind me, I will sing for you in class. That's, always a crowd pleaser. It's from Frozen. Now, this next piece is kind of important information to us in pre-calculus. The initial side of an angle in trigonometry is located on our positive x-axis. Okay, that's always the initial side of our angle. The terminal side is where it is ending. So in the case here, we have in this first example, here's our terminal ray in blue. And then we also have in the second example, the initial and then our terminal ray in blue. Now notice we could go counterclockwise or clockwise. So going this way is counterclockwise, and then the bottom is an example of rotating clockwise, right? Down like this would be our clockwise, like a standard analog clock that we don't see very often, okay? So these three vocabulary words are extremely important, not only in this lesson, but we will use them throughout Unit 3 and beyond. Now, at the bottom of the page, you see for number 2 that we have to draw a couple of these. So there's some space at the bottom of page 187 that I would recommend drawing is in. And the first is a representation of 1/4 of a complete counterclockwise rotation. So again, that's when we're starting here at our initial side, and 90 degrees would give us that beautiful right angle that we talked about earlier. Now, a 1/2 complete clockwise rotation would have us starting on the initial ray, and then moving counterclockwise would be then our terminal ray. Now, going in that counterclockwise direction is going to lead us to have a negative angle measured. This would be measured at negative 180 degrees in that clockwise rotation. Now, one complete counterclockwise rotation all the way around, well, it's like we're passing through 4 right angles. And basically what's happening is we have a full 360 degree rotation back to where we start, and it's positive 360 because we went counterclockwise. Next in part D, we have 1/8 of a complete clockwise rotation. So a clockwise rotation again is going to bring us down, and 1/4 is 45 degrees. And because we went clockwise, we would make it negative. And finally, our last example that is a little on the tricky side is 2 1/3 complete counterclockwise rotations. Well, again, we're starting at our initial ray here. If we're going counterclockwise 2 times, we would want to represent that as so. Now, 1/3 of 360 is 120 degrees. So that's going to place us here into quadrant 2. And this would be a total of 360 plus 360 plus the 1/3, the 120, for a total of 840 degrees, positive, because it went counterclockwise. Okay? Now, moving on to page 188 then, we see another important vocabulary word at the top there, coterminal angles. We will use coterminal angles a ton in this unit. And what basically happens when an angle is coterminal, you have either added or subtracted 360 degrees to your angle. Okay, there are an infinite amount of coterminal angles because you can go around and around that circle clockwise or counterclockwise as many times as you like. Right, so there'd be an infinite number of coterminal angles. And again, very important vocab word that we will use a lot. Now to look at that in the examples, if they are asking us to come up with 2 positive and 2 negative coterminal angles, we would want to add or subtract 360 n number of times that would make that possible. So if we add 360 degrees to 60, we end up with 420. That's a positive coterminal angle. And if we add another 360, we get 780. Now, if we were to subtract 360 from 60, we would get negative 300 and negative 660 as possible answers. Okay. Now, in number 4, they want us to specifically have an angle that is coterminal to the given angles that's between 0 and 360. And that's super important to us because a lot of times that makes it easier to graph since it would kind of be in the same position each time. So if we subtract 360 from 890, it's still not enough to get the appropriate answer. So we would want to make sure we subtract it enough so that we would be able to make it between 0 and 360. So in this case, you would take 890 and subtract 360 twice to be able to actually get the coterminal angle of 170. Same idea with part B. You would need to keep adding 360 enough times that you would get this between 0 and 360. So we end up having to add it 4 times to get positive 90 degrees. That's actually in the parameters that we want. Okay. Now, the last big part of this lesson talks about arcs. And arcs are going to be especially important tomorrow when we start talking about radians. But some formulas from back in your geometry day are the circumference of a circle, which is 2 pi r, or pi times the diameter, r is the radius. And then we also have an arc length formula, which is n divided by 360 times the circumference, because you're taking a fraction of your circumference when you're looking for an arc length. So if for the next couple of examples, we are looking to find the arc length here, we would take the angle measure, n, divided by 360, and multiply it by 2 times pi times the radius. We type all of this into the calculator as is, and we're going to just look for the decimal approximation here. And use your pi button to get the most accurate representation, and we get an approximation of 8.38 inches would be the approximate length of this arc. Try the next couple examples on your own. Now, if we look at the next page with number 6, okay, it says that we have a hand on a clock that is 6 inches long. So again, if you think about how a clock works, the hand on the clock is acting basically as our radius here. So we're kind of saying this is 6 inches long. Now, if it rotates around for 4.5 minutes, how many degrees is this going to travel? Well, 1 minute is a 360 degree rotation. So essentially for 4.5 minutes, we rotate 360 degrees, aka 4.5 rotations around our clock, which lead us to have 1620 as our value. Okay. Now, using that information, we can calculate then, again, that arc length by taking the degrees divided by 360, and then just times 2 pi r, which is 6. Okay. And that will give us an approximation of 169.65 inches. Okay. It would be our total distance traveled because it traveled around our clock for 4.5 times. Okay. All right. one last piece to be careful of when we talk about a major arc, we want the length of this big arc versus the minor arc, which would have been the small arc AB. So in this case, we went 180 and then another half of a unit of a quadrant, which would be a total of 225 degrees. And again, using our arc length formula, we could plug that in and get our final answer here of 19.63 units. Okay. And again, that's just found by putting this into the arc length formula. And in this case, our R is found by counting here our units. All right, we'll work more with this in class. Thanks, everybody.